Welcome in Dark Core. Astronomers once thought was the most distant single star ever observed. Its light traveling 12.9 billion years, first captured by the Hubble Space Telescope. But new observations from the James Webb Space Telescope suggest it may not be a lone star at all, but a compact cluster. Whether star or cluster, Earendel is reshaping how we view the universe's first billion years. In this video, we'll explore how the discovery was made, what JWST has revealed, and why its true nature matters for our understanding of cosmic dawn. The discovery with Hubble Earendel's story began in 2022 when the Hubble Space Telescope captured an unusually bright pinpoint of light along a distorted arc in a distant galaxy nicknamed the Sunrise Arc. This galaxy sits at a redshift of about 6.2, meaning we observe it as it was roughly 900 million years after the Big Bang. The brightness of this faint source was not due to its size alone, but to a cosmic coincidence. A massive foreground galaxy cluster sat between us and the Sunrise Arc, acting as a natural telescope. Through gravitational lensing, the gravity of the cluster bent and magnified light from the background galaxy. In Earendel's case, the magnification was extreme, boosting its visibility by more than 4,000 times. Without this alignment, Earendel would have been invisible even to Hubble. But with the amplification, astronomers were able to study its light and estimate its properties. The simplest explanation was that Earendel was a massive individual star, perhaps 50 to 100 times the mass of our Sun. That interpretation made headlines. Earendel was declared the most distant star ever observed. Beyond the record itself, the discovery carried deep implications. A star from this period could offer rare insights into the universe's earliest stellar populations, including potential analogues of population 3 stars, the hypothetical first generation of stars made almost entirely of hydrogen and helium. Even then, astronomers knew Hubble couldn't prove if Earendel was one star or many. The image was simply too blurred. The mystery had to wait for sharper eyes. And that chance arrived with the launch of the James Webb Space JWST revealed telescope. When JWST observed Earendel, astronomers gained access to both deeper images and spectroscopic data. Using the NISPEC instrument, they obtained a spectrum across near-infrared wavelengths. Unlike simple images, a spectrum shows how brightness varies with wavelength, allowing comparisons with models of stars or clusters. The results were surprising. Earendel's spectrum did not clearly match the profile of a single massive star. Instead, it could also be explained by a compact star cluster composed of several stars bound together by gravity. These models suggested a population with low metallicity, a term for stars with very few elements heavier than hydrogen and helium. That's exactly what astronomers expect for early stellar systems formed when the universe was still chemically young. At JWST's resolution, the light from a lens star and from a compact cluster can appear very similar. So, a definitive classification remains difficult. But the absence of certain spectral features tied specifically to hot massive stars raised doubts about the single star hypothesis. Another test lies in microlensing, temporary fluctuations in brightness caused by smaller masses crossing the line of sight. A single star should show sharper variations while a cluster's light would remain steadier. Continued monitoring of Earendel's brightness is expected to provide more clarity. JWST shifted the balance of evidence. While it hasn't ruled out the possibility that Earendel is a lone massive star or even a binary system, the data lean toward it being a compact cluster, a shift that could change how we understand the universe's first stellar systems. Why it matters, a debate over Earendel's nature matters, because each possibility tells a different story about the universe's first billion years. If Earendel is a single massive star, it remains the most distant one ever observed. That would make it an unparalleled probe of early stellar physics, possibly providing clues about the elusive population 3 stars. These first-generation stars are thought to have been extremely massive and short-lived, driving the chemical enrichment of the cosmos. If Earendel is instead a compact star cluster, it would be the earliest such cluster ever detected. This would show that groups of stars were already forming dense-bound systems in the early universe. Such clusters likely played an important role in cosmic reionization, the process that made the universe transparent to light, and may have survived to the present as ancient globular clusters orbiting galaxies like our own. The case of Earendel also highlights the power and limits of gravitational lensing. Rare alignments allow astronomers to study extremely faint and distant objects at levels of detail that no current telescope could achieve alone. But they also introduce complexity. Magnified points of light may hide multiple sources. Learning how to distinguish between stars and clusters in such data is crucial for interpreting other lens discoveries. Finally, the evolving story of Arendelle illustrates how science progresses. Initial data pointed strongly toward a star, but new observations broaden the interpretation. Rather than diminishing the discovery, this process reflects the reality of astronomy. Each new instrument sharpens our view and refines our understanding. Outro Arendelle remains one of the most fascinating finds of the past decade. First hailed as the farthest star ever observed, it now appears more likely to be a compact cluster of stars, a finding that deepens our understanding of how stellar systems formed in the young universe. But its light traveling nearly 13 billion years makes it a rare glimpse of cosmic dawn. As new data arrives, this tiny point could rewrite our view of the early universe. Subscribe to stay updated on the discoveries shaping our cosmic story. Thanks for watching Dark Core.